Hi everyone. In this Connect with Networking video, we're going to discuss wide area networks. Let's go ahead and get started. Wide area networks are quite a bit different than local area networks or backbone networks. The scale of a wide area network is typically miles in distance or more. They might span an entire city or an entire region of a country, or maybe even across multiple countries. And because of the scope and scale of a wide area network and the lack of ownership of the various geographic areas that we might be trying to span, most of the time companies don't own their wide area network infrastructure. In most cases, we're going to be using leased circuits that are provided by common carriers. So we'll be leasing equipment from companies like AT&T or Sprint in the US, or their parallel companies in other areas of the world. There are three common approaches to how common carriers provide their services for data distribution. One is a dedicated circuit network, another is a packet switched network, and a third choice is a virtual private network. And we're going to discuss all three of these various approaches. The first and oldest type of wide area network common carrier service is a dedicated circuit network. This uses a full duplex circuit that the common carrier provides via a leased or private line. A company that uses a dedicated circuit network is leasing the equipment from the phone company. They're not actually owning any of the equipment, but because they are leasing a specific line, it's as if they have their own private network. No other businesses are allowed to use that specific infrastructure. So the data that's flowing along a particular copper or fiber optic line is only data that belongs to the company, no one else's. So it's very secure and very private. A leased line is going to be charged at a flat fee per month. The telephone company isn't going to monitor what kind of data is flowing along that particular circuit, and they're not going to police the amount of bandwidth that a company is using. Of course, there is some maximum capacity that's available, but if you don't use up the capacity that's available to you, that doesn't matter. You're spending a certain amount of money every single month or every single year for the circuit that you are leasing, and you can use it or not use it as you see fit. Adding or removing lines or increasing or decreasing the capacity of a leased line situation can be difficult and time-consuming, but generally speaking, companies still tend to lease exactly what they need at a given moment in time, and if they need more bandwidth in the future, then they renegotiate their contracts with their common carrier. Pictorially, what we're talking about here is a variety of different ways to connect to our common carrier network to use a specific leased line connection between two different destinations. So the connection might be through a modem using some sort of dial-up connection, but through a dedicated circuit. It might be using some sort of multiplexer or some sort of channel service unit or data service unit. The specific types of equipment are usually not under the control of the company that's leasing the line. The equipment is going to be provided by the common carrier. So how you connect to their network and how you use your dedicated leased circuit is not really in your control. The common carrier dictates the terms, charges a specific flat fee, and you get the bandwidth that you're asking for. When a company pursues a dedicated circuit network, they can pursue a variety of different architectures to provide robustness and speed. And the three we're going to look at are ring, star, and mesh. A ring architecture is exactly what it sounds like. You can see in this case that every node on this wide area network has two avenues to leave that node and reach other nodes on the network. So it does provide some robustness, but not a lot. And it doesn't necessarily provide the most direct route from one place to another. An alternative to a ring-based architecture would be a star architecture, where everything flows from the various satellite nodes to one central routing computer in one location. In this case, connecting from any node to any other node takes 2 hops, which is probably faster than a ring network, but it does create a specific bottleneck location. If anything goes wrong in the Toronto location in this picture, then the entire wide area network would fail. If robustness is an important component of your wide area network, a company might pursue a mesh design. A full mesh would be every single node on a network connecting directly to every single other node in the network, as illustrated in the top of this diagram. You can imagine this is a very expensive solution, but if you are concerned about making sure that every single node on the network has the fastest connection and also has a variety of different choices in case a particular connection fails, this would be the best choice. But in most cases, companies will come up with some sort of compromise, even if they're pursuing a mesh architecture. A partial mesh, as shown in the bottom of this diagram, gives each node 3 or 4 different connections to other nodes on the network. So there's some robustness, there's some increased speed, but there's not the overall cost we might see from a full mesh network. Telecommunication companies in North America have traditionally provided 2 different types of dedicated circuits. The first and oldest is the T-carrier network, which is predicated upon old telephone wires. The newer dedicated circuit service is synchronous optical network, sometimes called SONET. T-carrier services is still the most common dedicated circuit used in North America. It uses copper wires, and it uses multiplexing to combine multiple copper wires up to a point where you receive the bandwidth you're looking for. So a unit of T-carrier services would be something like T1, which provides 1.544 megabits per second, which really isn't very much bandwidth, but for some wide area network purposes, this amount of bandwidth might be adequate. If you're just trying to keep 2 different servers in sync with one another, for instance, you might not need a lot of bandwidth. Bigger networks that demand more bandwidth could use larger units of the T-carrier services, like a T3 line that allows for 44 megabits per second. But the most common we see at the commercial level are T1 and T3 lines. In more modern pursuit of wide area networks, many companies have moved to optical carrier. The synchronous optical network, or SONET, allows for much greater speeds across vast distances. The units start at 51.84 megabits per second and increase up into the 10 gigabits per second. And of course, companies can pursue multiple 10 gigabit per second channels if they need even more bandwidth. This has become a very popular option for larger organizations that are moving a vast amount of data across the country or internationally. An alternative to a dedicated circuit would be a packet switch network, which operates much more like the traditional local area network or backbone network that we've studied in past chapters. A common carrier is going to use some sort of packet assembler and packet disassembler to move messages across their common carrier network using something that resembles the TCP/IP network that we've studied in the past. And customers would pay a fixed price for a connection to the carrier and then a variable fee for the amount of data that they're transmitting. So this becomes a very interesting solution for companies that have a lot of variable data exchange, where 1 month they're not sending that much information and another month they're sending a lot of information. You might see some significant cost reduction if you pursue this packet switch network. The common carriers like the packet switch network because it allows them to interleave messages from different organizations on the same circuit to provide maximum efficiency for their infrastructure. So they're seeing a flattening of the demand on individual circuits where sometimes one company is using more than another, but overall the aggregate amount of demand is fairly steady. And this allows them to get the most bang for their buck for the infrastructure investments that they've made over time. It's possible to ask for a permanent virtual connection on a packet switch network. You're still taking advantage of the packet switched architecture, but the circuit you are using to communicate from one place to another is effectively a permanent circuit, much more like a leased line. So this is an interesting compromise. But if you truly want the cheapest option, a switched virtual circuit that changes dynamically over time based upon what the common carrier wants and needs is definitely going to be the most affordable option. Customers can specify the rates they're looking for in a packet switch network. And typically common carriers will provide a committed information rate, which is going to be the minimum bandwidth that they are guaranteeing for the user. If you don't use up all that bandwidth, that's obviously fine. If you exceed that maximum allowable rate, it's possible that some of the packets will be discarded as the network becomes overloaded so that the common carrier can provide the committed information rate for all of their customers. Keep in mind this is very different than what consumers typically experience with their internet service providers. For an individual consumer, we typically have a maximum rate that the company will provide to us, but our internet service provider often doesn't guarantee a minimum. So while you might have a number that you're hoping to see in terms of your available bandwidth, you might be much lower than that during times of peak usage. So when we're talking about a packet switch network for a company, we're often able to get a guaranteed minimum rate, which is not something we're used to as individual consumers. Packet switching allows interleaving of packets from various pieces of equipment to intermingle with one another as they flow across the common carrier. In this picture, you can see different types of packets flowing from city node A to city node B, which will allow for a much more even flow of data on the common carrier circuits. So they like this flattening of the demand curve for their infrastructure. This does mean that when you're using packet switching for your common carrier, your information is intermingling with potentially other companies' information, which does allow for some potential concern in terms of security and might require you to use some sort of encryption to protect your data. Packet switch services have used a variety of different protocols over time. One that we've used in the past is frame relay, but we have seen an uptick in the use of Ethernet for packet switch networks at the common carrier level, which is interesting because that means that there's a transparent transaction from endpoint to endpoint, where every single part of the network is using Ethernet. And there is a new protocol called MPLS, which some common carriers have pursued to try to improve the speed that we might have seen over traditional frame relay networks. Frame relay is a layer 2 standard that has been used for mainframes and then was used for wide area networks in the past. So it is still used in many situations, but its usage has been steadily declining. It was designed for high performance and efficiency, but it does not provide any error control, so it's a bit unreliable. Ethernet has been widely adopted at local area network and backbone network layers, so moving it to the wide area network protocol is interesting. If we use Ethernet at the wide area network layer, we don't have to convert to a different protocol, which speeds up communication. When we use Ethernet, it allows the telephone network to bypass the old public switch telephone network, which means that this choice might be less expensive than some of the other alternatives and certainly much more efficient. The third possible option is MPLS, which is an abbreviation for multi-protocol label switching. And this has sometimes been called a layer 2.5 protocol because it does add additional information just above the Ethernet layer, but it isn't quite as serious and as complicated as the layer 3 internet protocol that we see on our overall network. So adding some additional information between layer 2 and layer 3 allows packets to be switched faster than using a routing protocol using IP addresses, but still using something that's slightly more robust than Ethernet. This is an interesting solution, and only time will tell whether this becomes more or less popular than moving to Ethernet. A third alternative for a wide area network would be to adopt a virtual private network. And in most cases, organizations use virtual private network as a supplement to either the leased line solution or the packet switch solution. This is something you can do in addition to those other two possibilities. What a virtual private network allows you to do is use encryption so that you can use a public internet connection between two devices and treat it as if it were a private packet switched network. Encryption allows you to send signals over something that is not typically secure, but because of the encryption, you can pretend that it's secure, and you can entrust that data to the wild, wild west that is the internet. Virtual private networks can be implemented at either layer 2 or layer 3, depending on what type of security you're trying to pursue. Often when we are connecting our various offices using a virtual private network, we refer to the connection as a VPN tunnel. I've never been crazy about this visualization because it suggests that the internet at large can't see the information that's being broadcast from one place to another, and that's not technically true. If you were eavesdropping on a connection on the internet, you absolutely could see packets flowing from one office to another. However, if you read deeper into those packets, you would encounter data that was encrypted, and therefore you wouldn't be able to make any sense of the information that's moving from one place to another. So the tunnel doesn't actually obscure the view of the data, it just makes the data that you can see unreadable. Virtual private networks are a great choice for things like intranet, where we're trying to provide internal network resources remotely. It's also correspondingly a great choice for extranet, where we're giving internet access to specific organizations that are outside of our organization, like our customers and suppliers. A third use of VPN would be Access VPN, so that our employees can access our organization's networks, things like file shares and print shares, from their home offices or when they're traveling for business. Virtual private networks add some additional packet information to the data that's flowing across the internet via an internet service provider. This picture shows how the client could be using VPN software and the office could be using some sort of VPN hardware to encrypt and decrypt signals from one device to another to fully protect the information that's flowing, even though the internet is inherently insecure. The biggest advantage of VPN is it is very inexpensive and very flexible. Almost any device could install VPN software and then take advantage of the encryption that it provides. But the downside is if you're relying on the internet to broadcast your information from place to place, you have no guaranteed data rate, so the traffic can be very unpredictable. And there could be some issues with incompatible implementations of equipment, hardware, and software. Not all vendor equipment and services are compatible with one another, so VPN still can sometimes present a challenge in this area. How you choose the various approaches for your wide area network depends on what you're trying to get out of your wide area network. If you're most concerned with speed, then a SONET dedicated circuit service might be your best choice. But of course, the cost is going to be very high. If you are concerned with some sort of middle ground where you get reasonably good speeds for a reasonable cost, pursuing something like Ethernet or MPLS, if your common carrier provides it, might be a good choice. If you're most concerned with keeping costs low and providing flexibility to your users, a VPN would be a good choice. And like I said earlier, you can always mix and match these various solutions depending upon the needs for specific parts of your business. Unlike the previous chapters where we talked about performance improvements, wide area network performance doesn't have as many options. We don't control the devices that are operating on a wide area network. The common carrier does. So we don't really have much control over making improvements to the equipment. And similarly, we don't own the circuits. We're typically leasing the circuits, and so we can't control the speed of those circuits. What we can do as organizations is lease more bandwidth if we need it and pay for it as needed, and add additional options like VPN to increase flexibility and perhaps offload some of the bandwidth that we need for our wide area network. And that is the one area where companies have control, is demand. If you're finding that your wide area network isn't performing as needed, shifting demand to off-peak hours or shifting demand to multiple channels like a dedicated circuit for your servers and a VPN for your individual clients might overall improve performance for your wide area network. The big implications for management are whether to consider Ethernet or MPLS over the traditional models we may have seen in the past, whether or not to consider leased circuits versus packet switched or VPN, and how to mix and match these various choices to give our users and our partners and our customers the best possible experience on our network. Similar to what we've seen in local area networks and backbones, we're seeing increased standardization and commoditization for the equipment and the software that is used at the wide area network level. So this is becoming an easier choice and a simpler choice from a standard and protocol standpoint. That's it for this chapter. Thanks so much for watching. See you next time.